The next section of the book here deals with norm, distance, and dot product. In this video, we want to take a look at firstly norm and then distance. We'll move on to the dot product in future videos. Now, when we think about vectors geometrically, mainly in R2 and R3, it's pretty straightforward as to say what we mean by length and angle. Just take your ruler out and measure the length of a vector, and if you got two vectors you want to know the angle in between them, well, you just take out your protractor and measure the angle, right? There's geometric tools to measure those geometric concepts. But what happens when we are thinking of vectors as pairs or triples of numbers, or in Rn it would be, of course, n-tuples of numbers? How do we talk about the length, right? If we've got a vector 3, 4, right? It's just a pair of numbers. What do you mean by the length of that? Or what do we mean by the angle between a couple of two different vectors? Right? We will come back to the angle between vectors once we've talked about the dot product. So in this video, let's just look at what do we mean by the length. Okay. Now, we have a way of pairing our geometric and our algebraic notion of vectors. So for instance, the vector there, 3, 4, can be represented geometrically by a vector whose initial point is at the origin and whose terminal point is at the point 3, 4 in that, that Cartesian xy plane. Right? And so then we associate with that algebraic concept, 3, 4, to the geometric vector, that length, that directed line segment. Okay. Now, we can then take out a ruler and measure it, but we also know that we've got some tools to use. For instance, if this vector here, vector v, is in standard position, I know that the first entry in the list, the pair of v1, v2, that first entry is the length from the origin horizontally to just below where the endpoint of the vertex is. Likewise, v2 is the distance from the x-axis up to that point, so v1 and v2. This would be a right angle right here, and we have a right triangle, and we can use a very geometric theorem called the Pythagorean theorem, which tells us that the length of this side squared plus the length of that side squared is equal to the square of the diagonal. Now that the length of the diagonal is exactly what we're looking for. So the length of the diagonal is the square root of v1 squared plus v2 squared. Notice the notation that I have here of the double absolute value sign around the vector. This is what we're going to call the length of the vector, or the norm of the vector. I'll talk about the difference between norm and length here in just a minute. But likewise, if we're in R3, right, this vector here I drew was in the plane in R2, but we could have been in 3D, in which case we would have three components, v1, v2, and v3. So in R3, you'd have some vector here, which you'd have an x component, a y component, and a z component, and you could see, well, if this is v1 and this is v2 and vertically here is v3, that from here to there would be the square root of v1 squared plus v2 squared. But then you'd have another right triangle here, where that's a right angle, and this thing squared plus v3 squared would be the square of the length that we want. Well, the square of the square root there just gets rid of both of them, and you end up with this formula right over here, that the length of that vector is the square root of the sum of the squares of the components, right? This formula and this formula are both algebraic representations of what we would mean by stick your ruler on it and measure it, right? I don't have a way of sticking a ruler and measuring on 3, 4, but I can say, well, I can do the square root of 3 squared plus 4 squared, And that would be the square root of 9 plus 16, which would be the square root of 25, which is 5. And I would know that the length of that vector is 5. And I could verify that by putting a ruler on it. Okay. Now, let's move down the page here a bit. And let's look at a definition. Okay. If we have a vector v in Rn, then we say the norm of the vector is given by this. Now I'm going to use the notation of the double absolute value sign, which in previous videos I'm pretty sure we've used to mean the length of vector. I'm calling it norm of vector. Well, actually, the book is calling it the norm of the vector. And it is the sum of the squares. It's the square root of the sum of the squares of the individual components, right? v1, v2 up to vn are the n components of that vector. Notice it is in R2 it's the same formula with just 2 components. In R3 it's the formula with 3 components. In R4 you'd have 4 things added up in there, and so on. This textbook goes to great pains to say that they can see what geometry means in R2 and R3 and use geometric reasoning, but as soon as you step into R4 or R5 or some higher dimension, they say, we don't know that geometry works the same way. And so they try not to rely on geometric arguments. Likewise, they wouldn't ever call this, the textbook we're using, doesn't ever call this the length of the vector in Rn. They call it the norm of the vector. Now, when you go on in math and you take, a higher level linear algebra class, you'll find that the concept of norm is bigger than just this. There are other things that they call norms, and all norms would have to satisfy certain properties, and this is one of the examples of a norm. But it is the example of the norm that corresponds to our notion of length geometrically. Okay. So sometimes this is actually called the Euclidean norm because it calculates length as Euclidean geometry would interpret it. Okay. Anyway, I will interchange in my own language length, norm. They both mean the same to me in this context within this class. I'm also one that disagrees with the book in that we can't say what's going on in the geometry in R4 and higher. It's just like a point is still a point, a line is still a line, a vector still looks like a vector, it's just stuck in a different dimension. They behave the same way, and the book essentially proves they behave the same way. But anyway. So here's an example of the norm of a vector in R4. I've got the vector 1, 2, 3, 4, and I just take the square root of 1 squared plus 2 squared plus 3 squared plus 4 squared, which is the square root of 30. So the length, I would say the length of that vector is the square root of 30. The book would say the norm of that vector is the square root of 30. Now, notation. Some textbooks use just an absolute value of the vector as opposed to the double absolute value to indicate length or norm. And because I'm typing up all my notes, I will probably always use the double, but when I'm writing it down, I generally just use absolute value to indicate length. I mean, the context that I'm not taking the absolute value of a vector. I take absolute values of numbers. So to put absolute value around the vector means something different. Just as when I put an absolute value around a matrix, it meant take the determinant, right? Now I might say that absolute value on a vector means take the length of the vector or the norm of the vector. Okay. You will see both notations within the literature. Our textbook sticks pretty closely with the double absolute values. But I want to take a look at how these really are, in some sense, the same notion. Because if you look at R1, which would be just single numbers, or you don't have, in R2 you have pairs of numbers, in R3 you have triples of numbers. Well, in R1 you just have each vector is just a number, right? It's a list with one number in it. So for instance, if the vector here is just A, and we calculate the norm of the vector, well, I'm going to take the sum of the squares of all the components of that vector, and then once I've got them added up, I'm going to take the square root. So it's the square root of a squared, which, if a is positive, is equal to a, but if a was negative, you'd be getting the negative of a, and actually the square root of a squared is the absolute value of a. So the notion of norm in R1 is exactly the same as the notion of absolute value, right? There's the question of, are the vectors here lists of things with only one number in it, or are they just one number, right? You can interpret it either way, but the norm plays the same role as absolute value does. Now, theorem. The norm is always greater than or equal to 0. This is clear. In R2 and R3, if you think of length, yeah, the length of the vector is always positive. The smallest it's going to be is 0 for the 0 vector. But this is a theorem that even in Rn, where we don't necessarily know what the geometry is, sorry, something just jumped around here. Where am I? I want to get the definition on here up here. So yeah, I mean, it's certainly greater than or equal to 0 because it's defined as the positive square root of something. I don't even care what's inside. It's the positive square root. So this is always greater than or equal to 0. Now, if I look at the inside, that this is saying that the norm of a vector is equal to 0 if and only if the vector is the 0 vector. Well, if and only if means there's an implication both ways. If this is true, then that has to be true, and if this is true, then that has to be true. So I think it's easiest, one way is if you got the 0 vector here, that means all the components are 0, and sure enough, if you square a bunch of zeros and add them up, you're going to get 0. You take the square root, you get 0. So certainly the norm of the 0 vector is 0. But also, if you know that you've got a vector whose norm is equal to 0, this is a sum of positive, at least non-negative numbers here. And the only way that this could add up to 0, the V1 and V2 and whatever, they could be positive or negative, but when you square them, you're getting positive. So the only way this could add up to 0 is if all of the things you're adding are equal to 0. And so if you know the norm is 0, the length is 0, then it must have been the 0 vector to start with. Okay. And then finally, the theorem is saying if you multiply v by a scalar k, since k is just a real number, then the length of that, the norm of that, is the norm of the vector you started with times the absolute value of k. And we've talked about this when we introduced the notion of scalar multiplication, right? That what does it do? It multiplies the length by k. And in Rn, scalar multiplication multiplied each of the components by n. Now, the textbook has a proof of part C, and I will leave it to you to read that. It's just simple plug and chug and see that when you plug a k, you multiply each of the components by k, and then square everything, and then the k squareds factor out, and you end up with this here. Okay, so multiplying a vector by a scalar scales that vector by the length, scales it by the amount equal to the absolute value of k. Okay. Negative k's, of course, turn the vector around, but the length of them would be the same. I mentioned earlier in this video that the concept of norm is actually a broader concept. And when you get there, you'll find that this theorem is actually what they use as a definition. They say a norm is any, I'm going to call it a function. A norm is any function that takes vectors as inputs and real numbers as outputs that satisfies these three properties. That when you plug a that you plug any vector in, you're going to get something out that's either 0 or bigger. And the only way you get a 0 is if you plug 0 in, the 0 vector in, and likewise if you plug the 0 vector in, you get 0. And if you multiply any vector by a scalar and then plug it into your norm function, that what you get out is the norm of the vector times the absolute value of k. Anything that satisfies these three properties is what is called a norm. And so this theorem is really just saying that, hey, this thing that we're talking about is a norm in a much broader sense. But from the point of view of this class, you don't need to know that there's a broader sense. I like to point it out so that it's not a surprise to you when you get there. Now that we have a notion of length, we have a notion of a unit vector. And a vector is called a unit vector if it has length 1. Okay? And notice that if we start with any vector, any non-zero vector, we can always scale it to be a unit vector. That is, because of this property right here, if I multiply a vector times some scalar, and the length is just a number, so 1 over that length is a number. So this is a number I'm multiplying by the vector v. The length of this thing would be the absolute value of this positive number times the length of this vector. So I'd have 1 over the length of v times the length of v, which would just be 1. And so any vector can be scaled up or down to be of length 1. There are some textbooks that define the direction of a vector to be the unit vector pointing in the same direction, right? That is, what's the direction of vector v? It's this unit vector u. The 1 over the length of v is a positive number, so I'm not changing which direction the thing's going. I'm just scaling it down to have length 1. And in many textbooks that I've seen, that's what they actually define as the direction of the vector v, this unit vector. So for instance, here's the vector we looked at up above, the vector 1, 2, 3, 4. We noticed that its length was the square root of 30. So if I take 1 over the square root of 30 and multiply it by this vector, then I get this one right here, 1 over the square root of 30, 2 over the square root of 30, 3 over the square root of 30, 4 over the square root of 30. That vector in R4 has length 1. Now, standard unit vectors. In R2, we have two vectors that we call the standard unit vectors, the vector 1, 0 and the vector 0, 1. This one pointing in the direction of the x-axis, that one pointing in the direction of the y-axis, I and j. We have similar things in R3, where I is 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. I want to point out that I'm a little disappointed, disappointed is not quite the right word, that they use the same letters here and there, because this I is not the same as that I. This first I up here is a list of two numbers. It's 1, 0. Okay. This one down here is a list of three numbers, 1, 0, 0. They are not the same. Now geometrically they feel the same to us because we're so used to drawing those coordinate systems, either the XY coordinate system or XYZ, and pointing in the direction of the x-axis is what both of those two I's do, which is really why they have the same name. But they're different vectors. They're not the same thing. Okay? They're in different spaces. This one's in R2, that one's in R3. Likewise for J. Notice that any vector in R2 can be written as a linear combination of I and j. Remember, linear combination means a sum of multiples. So if I have the vector AB, I could write it as A times I plus B times j, where A times I, of course, is A times 1, 0. That would be A0, because the 0 times A is still 0. Likewise over here, B times j would be 0b, and A0 plus 0b is, add them component-wise, you get AB. So certainly it can be written as a linear combination of those two. Again, linear combination means I've multiplied each one by a constant and I've added the results. Okay. In R3, any vector can be written as a linear combination of I, j, and k. And in fact, any engineers who happen to be in this class, you may have done some stuff with vectors in some engineering classes, and engineers typically write their vectors in terms that look like this, as combinations of I, j, and k. I'm not an engineer, I'm a mathematician. I prefer to write them this way. I feel like it has less, less ink used. And I see this as a sum of three things, where I see this as a single vector. And that's just my bias on it, but definitely you will see this notation in a lot of possibly even physics books and engineering books. Okay, standard unit vectors. We could keep going and say, oh, in R4 I got I, j, k, and l, and then R5 I, j, k, l, m, and you're just going to run out of letters pretty soon. So generally what we do is we say, in Rn, I can still have a set of what are called standard unit vectors. and we use the letter E for whatever reason. E sub 1, E sub 2, E sub 3 are the n all the way up to E sub n here. These are the standard unit vectors in Rn. E1 has a 1 in the first position and zeros everywhere else. E2 has a 1 in the second position and zeros everywhere else. En has a 1 in the nth position and zeros everywhere else. Everything in between there would be, as you would expect, right? A 1 in the ith position and zeros everywhere else. Now, the last thing I need to talk about in this video is the notion of distance, the distance between two vectors. What the heck do we mean by the distance between two vectors? If I've got a vector u and a vector v, what's the distance between them? Well, what we're going to mean by it is actually the distance between, stick them in standard position, and look at the distance between the two endpoints. Right? So this distance right here. Well, that right there we have seen is either v minus u or u minus v. I think the way I have it drawn is v minus u. So the distance between u and v is going to be the length of v minus u. Well, to calculate v minus u, I have to component-wise say first component of u minus first component of v minus first component of u. Second component is second component of v minus second component of u. So that's what I see here. There's the difference of the first components, there's the difference of the second components, and so on. So when we talk about the distance between two vectors, we're just meaning the distance between the two endpoints. Anyway, we will move on to the dot product in our next video.